In this video, we are going to talk about absolute value inequalities. Let's review the absolute value of a number. The absolute value of a number is the distance from that number to zero. For instance, absolute value of 3 is equal to 3 because the distance from 3 to 0 is 3 units. Absolute value of negative 3 is also equal to 3 because the distance from negative 3 to 0 is also 3 units. Now, if absolute value of x is less than 3, then that can be interpreted as the distance from x to 0 is less than 3. So what this means is we want to come up with some number x such that when you measure the distance from x to 0, it has to be less than 3 units. So here's what it means on the number line. So we all know that the distance from 3 to 0 is 3 units, and the distance from negative 3 to 0 is also 3 units. So if we're looking at distance that is less than 3, we could be looking at 1 or 2. As you can see, distance from 1 to 0 is 1 unit, that's less than 3. And the distance from 2 to 0 is also less than 3. It could also be anything in between. Could be 0.5, could be 1.7, could be 2.3. There are infinitely many numbers in between here that will have the distance to 0 that is less than 3. The same thing could be argued for this side, where x could be negative 1, x could be negative 2, where the distance from negative 1 to 0 is 1 unit, that's still less than 3. The distance from negative 2 to 0 is 2, which is still less than 3. It can also be negative 1.3, negative 2.8, or anything in between negative 3 to 0 here. So with that said, we can conclude that for the distance from a number to be less than 3, we'll be looking at x is from 0 to 3, so x has to be less than 3. And at the same time, it could also be from negative 3 to 0, so x could be anything greater than negative 3 as well. So x could be anything in between negative 3 to 3. What if absolute value of x is greater than 3? That means the distance from x to 0 is more than 3 units. So on the number line, again, we're going to put 3 on one side, negative 3 on the other side. This time we want the distance to be greater than 3. So we could be looking at 4, 5, 6, 7, and so on all the way to infinity. We could also look at all the numbers, all the decimal numbers in between those integers. So anything to the right of 3 would be qualified for the distance being greater than 3. Distance to 0 is bigger than 3. And then, same thing could be argued for anything to the left of negative 3. Anything here will have the distance to 0 that is bigger than 3. So we're looking at two intervals that will satisfy the condition where the distance is greater than 3. We're looking at x could be greater than 3, or x could be less than negative 3. So in general, for any real number k, where k is greater than 0, absolute value of x is less than k. That means x has to be between negative k to k. So it looks very similar to what we came up with up here, where x is between negative 3 to 3. And then absolute value of x is greater than k. That means there could be two intervals, whether x has to be greater than k or x has to be less than negative k, just like what we came up here with x is less than negative 3 or x is greater than 3. So we're going to look at some examples. I put a little note here. We always want to isolate the absolute value first before we can try to get the variable by itself. So in example 5, we want to first add 3 to both sides. We're trying to isolate this absolute value first. So then we have 2 times absolute value of 6 minus m is less than 10. The negative 3 and 3 would cancel. We can isolate further by dividing both sides by 2. Since the 2 is on the outside, we can still isolate that absolute value a little more. So this will give you 5. So looking at this, it reminds me of the first scenarios where we have something in the absolute value that is less than a positive number. So instead of x, we have this whole expression, but we're going to apply the same concept where whatever is in the absolute value here, we're going to sandwich it in the middle. So 6 minus m is in the middle. And then on the outside, we should put 5 and negative 5, just like what we have up here with negative k and k. Now it becomes a 3-part compound inequality and, where we can get the variable by itself. So to get m by itself, first you're going to subtract 6 from all sides, from all 3 sides. So we got negative 11 on the left, negative m in the middle, and negative 1 on the right. We still don't have m by itself yet. We want to divide everything by negative 1. Now notice that we're dividing everything by a negative number. We want to flip the inequality signs. So now we have positive m in the middle, positive 1 on the right, and positive 11 on the left. We can interpret this as 1 is less than m is less than 11. I do prefer to have the bigger number on the right, so when I write an interval, it'll be a lot easier. We are going to graph this. So on the number line, we want to put the smaller number on the left, bigger number on the right. M is being sandwiched between 1 and 11. That means we're going to take anything between 1 and 11 here, and we're going to use parentheses for 1 and 11. Now, writing an interval, that would be anything between 1 and 11 and parentheses. Next, we have 2 times absolute value of 3x plus 1 is greater than or equal to 4. So first, I want to isolate the absolute value. And to do that, I need to get rid of the 2. So I will divide both sides by 2. Now, on the left, we are left with 3x plus 1 absolute value is greater than or equal to 2. Notice that we're dividing both sides by a positive number here, so we do not have to flip the inequality sign. This is the second scenario that we came up with earlier, where if x is greater than k, then we're looking at either x is greater than positive k or x is less than negative k. So we're looking at the expression that's in the absolute value is either greater than or equal to positive 2 or is less than or equal to negative 2. This becomes an or compound inequality. Now we will subtract 1 from both sides. So we have 3x is greater than or equal to 1. And then divide both sides by 3. We get x is greater than or equal to 1/3. For this one, we subtract 1 from both sides. We get 3x is less than or equal to negative 3. Then divide both sides by 3. We get x is less than or equal to negative 1. Now let's graph the solution. So we should have negative 1 on the left, 1/3 on the right. X is greater than 1/3. So we're looking at this section right here with bracket. Then x is less than or equal to negative 1. We're looking at this section on the left here and bracket on negative 1. So we're going to list all the intervals that has been highlighted because this is an OR scenario. So we're looking at negative infinity to negative 1. That will cover the green intervals. And then union with the red interval, which is 1/3 to infinity. There are some special cases that we need to look out for. So the first one, we have absolute value of x plus 2 is less than negative 4. Now, we already learned that this describes a distance. And if it is a distance, it has to be something that is greater than or equal to 0, because simply a distance cannot be negative. So we can't have something that is greater than or equal to 0 and less than negative 4 at the same time. So this statement actually doesn't make sense. So we can say there's no solution because absolute value can't be negative. Now this next one is the opposite. We have absolute value of x plus 2, which we know is always greater than or equal to 0. Well, if something is greater than or equal to 0, of course, it is always going to be greater than negative 4, no matter what. Now, when you see greater than or equal to negative 4, you really only have to satisfy one of the conditions, greater than or equal to. In this case, we definitely satisfy the condition greater than negative 4, so that should make the statement true. Because it is always true, the answer for this would be all real numbers, or you can say negative infinity to infinity. That would be the answer. This next one, we have absolute value of x minus 5 is less than or equal to 0. Now, let's break this up. So there are two things going on. Absolute value of x minus 5 is less than 0, or absolute value of x minus 5 is equal to 0. That's what it means when we say less than or equal to. It's really the two scenarios. With the absolute value of x minus 5 is less than 0, we already determined that that can't be true based on example 7, because absolute value of a number can't be negative. But the second part could be true. An absolute value can be 0. So if it is 0, we solve this absolute value equation. So either x minus 5 is equal to 0, or x minus 5 is equal to negative 0. But negative 0 is just 0, so we really just have one scenario here. Add 5 to both sides, we should get x is equal to 5. So x is equal to 5 is the only solution for this example. Next, we have x minus 5, absolute value of x minus 5 is greater than 0. So we remember that this absolute value can be greater than or equal to 0, but now we're saying that in this problem, the condition is it has to be strictly greater than 0. It cannot be equal to 0 at all. So it basically will be true for all real numbers except x is equal to 5, because when x is equal to 5, then the absolute value will be equal to 0, which we don't want, because we want the absolute value to be strictly greater than 0.